Hello everyone, welcome to lecture 49 of the NPTEL course on Riemannian geometry. So last time we introduced this notion of conjugate points. Let me remind you of what that was. So let us say I have a geodesic from the interval 0 to L to M connecting these points P and Q, and let us assume that gamma of t is given by the exponential at P of TV. Then we say that Q is conjugate to P along gamma if there exists a non-trivial Jacobi field along gamma which vanishes at the two endpoints. Okay. Alright, so we also saw an equivalent characterization in terms of the derivative of the exponential map. So this happens if and only if you look at the derivative of the exponential map at LV, note that Q is equal to gamma of LV, right, Q is equal to the exponential of LV, okay. Then Q is a conjugate point if and only if the kernel of the derivative of the exponential map at this vector LV is non-trivial, okay. And then we proved this baby version of the index theorem which says the following, that suppose you have an interior point T naught which such that gamma of T naught is a conjugate point to P along gamma. So that means suppose there is an interior conjugate point, then in fact we can find a vector field X that vanishes at the two endpoints such that the index, the corresponding quadratic form of the index at X is negative, is strictly negative. So in particular this implies that gamma cannot be minimizing, because we saw earlier as a consequence of the second variation formula that if gamma is minimizing, then this index form is positive is non-negative definite, right. So if we find a negative direction, then gamma cannot be minimizing. So the upshot is that geodesics cease to be minimizing beyond conjugate points. So natural question is that the only way that geodesics stop being minimizing, right. So the question that we would like to answer in this lecture is this the only way stop minimizing? And the answer is obviously no, because to illustrate why, let us go back to our example with the cylinder. Okay, so we had this the round cylinder with the usual product metric. We know that let us say you take any point P and any geodesic, right. So you take any, let us say any geodesic which in general are given by helices, then this has no conjugate points. Okay, so this is empty, sorry. Okay. Now on the other hand, suppose you take the following geodesic, you just take this the circle which remains at I mean it is basically the intersection of a plane at some height z equals h with the cylinder. Then you consider the following point P and point Q, right. Then clearly this circle will cease to be minimizing as it goes beyond Q, but Q is not a conjugate point because there are no conjugate points, right. So clearly the green geodesic, which I will denote by gamma, is not minimizing beyond Q, but Q is not in is not a conjugate point, okay. So here something else is happening, that you actually have two geodesics that come together at P at Q, right. So you of course have this geodesic, and then there is also this geodesic. Okay, both basically have both are minimizing geodesics from P to Q. So it turns out that this is essentially the only other way that minimization can stop. So essentially the only way your geodesic can stop being minimizing is either you encounter a conjugate point, or you have another sort of geodesic that another minimizing geodesic that comes together with your original geodesic. Okay, so we want to now make this formal. We want to prove this result. So I think I might have introduced this notation before, but in any case I will denote by SPM the set of all tangent vectors at P with norm 1. Okay. So here is a definition. So let theta be some unit tangent vector at P, then we define the cut point. So we want to quantify what we mean by the statement that this geodesic stops being minimizing beyond a certain point. So this is quantitatively captured in this definition. So we define the cut time of theta. So it is denoted by T theta. So this is the supremum of all t, so that if you look at the corresponding geodesic exponential of T theta, so maybe I will just for notational sake I will so this is minimizing on the interval 0 to t. Okay. So this captures the maximal time for which your geodesic with initial velocity vector theta remains minimizing. Okay, so of course this cut time could be infinite. So for instance, if you are working, so note that on Rn with the usual Euclidean metric, this is infinity for all theta, right, because on Rn the geodesics are straight lines, and straight lines are minimizing throughout there, right. So here for Rn the cut time would be infinite. So there is no reason why the cut time is finite. If the cut time is finite, so if T theta is finite, then we call gamma of T theta the cut point to P along this geodesic gamma theta. Okay. Okay, so the next proposition characterizes these sort of cut times. So proposition, so let this be complete, let P be a point in M and theta a unit tangent vector, and let gamma theta be the corresponding geodesic. Okay. So let T naught be a real number and let Q be gamma theta of T naught. Okay. So the first part is if T naught is the cut time, so that means Q is the cut point to P along gamma theta, then either of the two things happen. So, either Q is the first conjugate point to P along gamma theta, or as I said, you have two minimizing geodesics coming together, or there exists a unit speed geodesic, let us call it sigma, from 0 to T naught to M, such that sigma of 0 is sigma of T naught is Q, and sigma is not the same as gamma. So, it is a distinct, it is a different geodesic that that comes together at Q, and because T naught is T theta, gamma is actually minimizing, is the minimal geodesic connecting P to Q. So, the distance from P to Q has to be T theta, which means that the sigma will be another sort of minimal geodesic connecting P to Q. Okay. So, that is the first part. The second part is sort of a converse. So, conversely, if A or B holds, if either A or B holds, then the cut time has to be less than equal to T naught. Okay. So, the cut time, the geodesic has to cease to be minimizing before it reaches T naught. Okay. All right. So, let's prove this. So, let's prove the first part. So, suppose T naught is actually equal to the cut time. Okay. So, in particular, as I was explaining, T naught is precisely the distance from P to Q. Okay. So, let us draw a picture. So, here is P, this is Q. Now, because we are working on a complete manifold, this gamma actually keeps going on, right. All geodesics exist for all time. Okay. So, let Qk be equal to gamma of T naught plus 1 by k. Okay, and let Lk be the distance from P to Qk, which of course as k goes to infinity, because Qk's converge to Q, this distance will these Lk's will converge to T naught, right. But now because we are working on a complete manifold, by Hofrino you have your point Qk here, there exists a minimal geodesic connecting P to Qk. Okay. So, let sigma k given by T theta k, where theta k is some unit tangent vector, be the minimal unit speed, be a minimal unit speed geodesic from P to Qk. Okay. So, in particular Qk is the exponential P of Lk theta k. Okay. All right. Now, because these theta k's have unit norm, by the Bolzano-Weierstrass property for the tangent space or Euclidean space. So, the Bolzano-Weierstrass property implies that after passing to a subsequence, which we will continue to denote by theta k, which we will continue for notational convenience, we see that these angles, these tangent vectors converge to some theta infinity, okay, which is another unit tangent vector. So now there are two cases. So the first case is that this theta infinity is actually the original tangent vector initial velocity vector of gamma, okay. So in this case consider the following vectors. So consider the vectors Vk given by Lk theta k and Wk given by T naught plus 1 by k times theta. So why am I considering these? Because if you take the exponential of Vk, then that is Qk, right, but that is also the exponential of Wk, because this is simply gamma of T naught plus 1 by k. We had defined Qk to be gamma of T naught plus 1 by k, and this is precisely sigma k of Lk, right, and sigma k was the minimizing geodesic connecting P and Qk. Okay, so the situation is as follows. So let us draw another picture. So you have your P, you have your Q, and then you have these points Qk, okay. If you look at the corresponding picture in the tangent space, so let me do it this way. So you have the tangent space here, and you have the manifold here. Okay, you have this sort of vector which is given by L times theta or T naught times theta. Okay, that corresponds to this geodesic gamma from P to Q. Now you take a little neighborhood of this tangent vector in the tangent space. So note that each of the vectors Vk, this converges to T naught times theta, also Wk converges to T naught times theta. So you have this collection of two sequences Vk and Wk, whose map under the whose image under the exponential map is the same point, right, which means, so this tells you that the exponential map is not locally injective. Near this vector T naught theta. But then the derivative by the inverse function theorem, the derivative of the exponential map is not invertible. At this vector T naught theta. That means that there will be something in the kernel. Why? Because suppose it were invertible, then by the inverse function theorem the exponential map would be a local diffeomorphism, in particular it will be locally injective, that is a contradiction, right. But then if this happens, this implies that Q is a conjugate point by our characterization. Okay. So A is satisfied. So we started off with assuming that T naught is the cut time, and this limiting angle theta infinity is the original angle theta, and we concluded that A is satisfied. Let us look at the other case. Suppose this is not equal to theta, okay, then just consider the geodesic sigma of t given by the exponential of t times theta infinity. Okay. Then what is Q? My claim is that this is another geodesic. So, my claim is that sigma from 0 to T naught is a geodesic such that sigma of 0 is P, that is obvious from the definition, sigma of T naught is Q and sigma is not gamma. So, B is satisfied in this case. We have found two minimal geodesics connecting P and Q. Okay, why is this the case? That's simple. You just look at the limit as k approaches infinity of sigma k of Lk. Well, that is precisely, so sigma k of Lk is Qk, the limit of Qk is precisely Q, but on the other hand this is also the limit as k goes to infinity of the exponential map of Lk times theta k. So, I am assuming that theta k is converged to this theta infinity. So, this is precisely the exponential at P and Lk is converged to T naught. So, this is precisely sigma of T naught. Okay. So, sigma of T naught is Q, sigma is obviously not the same as gamma, since the initial velocity vector theta infinity is not the same as the initial velocity vector of gamma. So, this proves the claim. Okay, so now conversely, suppose A or B holds, or of course both can also hold together, they are not mutually exclusive. So, again we have two cases. Suppose A holds, okay, then in this case gamma cannot be minimizing beyond Q, right. So, clearly the cut time has to be less than equal to T naught, right, because gamma cannot gamma ceases to be minimizing beyond Q. Okay, so this is easy. What about the second case? Suppose B is satisfied, okay. So, in that case we know that there are two sort of geodesics connecting P and Q. So, this is gamma, this is sigma. So, now let us look at some point that is slightly beyond Q along gamma. So, for the sake of contradiction, suppose T theta is bigger than T naught. So if it's strictly bigger than T naught, we can squeeze in a little epsilon. So let us say for some epsilon positive. Okay, so then consider the following: omega t to be the path obtained by concatenating sigma t from 0 to T naught with gamma t between T naught to T naught plus epsilon. Okay. So then clearly omega t is also minimizing. Why is that? Let us go back to this. So clearly the length of omega t, so omega t is basically given by first following this and then following gamma. So clearly that length is also T naught plus epsilon, and the distance from P to this point is T naught plus epsilon, because we are assuming that that gamma, which is a unit speed geodesic, is minimizing from this to this point, which I will call Q tilde. Okay. So clearly omega is also minimizing, but then all minimizing geodesics have to be all minimizing paths have to be smooth. So this implies that omega is smooth, which in particular implies that that the two derivatives at this problem point T naught must match up. Remember, these derivatives make sense because gamma and sigma exist for all time, right? Since we are working on a complete manifold. Okay, but then by the existence and uniqueness of geodesics, since sigma of T naught is also equal to gamma of T naught, sigma has to be identically equal to gamma. Okay, so that is a contradiction. So again we see that T theta will have to be less than equal to T naught. Okay. All right, so that completes the proof of the proposition. So the upshot is that given gamma, it will cease being minimizing, it will cease to be minimizing beyond T naught if two possibilities hold: gamma T naught is a conjugate point, or we have this picture that you have two minimal geodesics connecting which join up at this point gamma of T naught. Okay, so that is the only two ways in which your geodesic will stop minimizing. All right, so that is it for this lecture. In the next lecture, I will use this characterization to give you essentially a maximal neighborhood on which one can define normal coordinates. Okay, so that's the content of the next lecture. All right, so thank you for your attention, and I will see you next time. Thanks.